In the previous video, I've discussed why is it really hard to get a closed form analytical solution to the equations of motion. However, if we do a few simplifications, we can find an approximate analytical answer, analytical solution to the trajectory a rocket will follow. Although that we're going to do a lot of simplifications, analytical solutions are of tremendous interest because we can understand how the variables are going to affect to our solution, even though the result isn't super precise, and we may have to move on to something more precise, another method, which will be more difficult to implement, but more precise when we want a final answer. But in analytical solutions, you shouldn't underestimate them or discard them at all. So let's see what simplifications we will have to do to the equations of motion, so we can find some analytical solutions. So the first simplification we're going to do is that the rocket is only moving vertically. So there'll be no oscillations, and therefore all the forces are on the roll axis. So the second simplification we're going to do is that let's see, the axial drag is going to be equal to a constant k throughout all the flight times v squared, the velocity of the rocket squared. Okay, so this isn't this is a bad approximation. I mean, we're going to do worse approximations here, so this is not too bad. The k, we're going to see how to find this value on future videos. All right. So another approximation we're going to do is that thrust is constant throughout the flight. Okay. We can design a rocket motor so that the thrust is constant, but in general, it's not going to be constant. And but yeah, to find this analytical solution, we're gonna suppose that thrust is constant. Then the most severe approximation is going to be that the mass is constant throughout the flight. Now this is a pretty bad approximation. So, but oh well, we have to. You'll see why we have to take this approximation, but we're going to have to do this to find an analytical answer. So we'll say that the mass is going to be the semi-sum of the initial mass and the final mass. So yeah, we have to choose something, so just choose the average. All right. So now if we take we only have one equation, which will be the Newton's law on the roll axis. It's simply going to be the mass times the acceleration. We're going to write it as the derivative of velocity in time equals the thrust minus the weight and minus the drag. All right. So if we send this on the other side, we can integrate. We have thrust here. What do we have there? We have mass kV. Okay, squared. This is dV. And on the other side we have dt simply. And you see here that why we have to take mass constant, thrust constant, and k constant, because we're integrating in dV and unless we have the massive function of TV, we're not going to be able. Oops, I still have this. We're not going to be able to integrate this. We're not going to be able to evaluate this. Let me see if I can delete this. All right, thanks. So if you do this integral and you integrate from velocity 0, so take off to the burnout velocity, and we're going from time equals 0 to time of the burnout, so the time that the motor stops burning. Okay. Well, if you integrate this, you're going to find that the burnout velocity is equal to square root g k, and here we have the hyperbolic tangent of time of the burnout. Time of the burnout, by the way, what is this? This means it's the time that the motor runs, the motor is firing. So so motor firing time. Okay, this can be, for solid rocket motors, is going to be really low. It's going to be high thrust, really low burning time. So for hybrids, it's normally longer firing time, longer burns. Okay, but for solids, it can be anything. Like the small solid rocket motors, the hobby ones, are maybe half a second, but you can have easily, I don't know, 30 kilo solid rocket motor that burns in, I don't know, 5 or 6 seconds. So yeah, they burn fast. So I haven't finished this. This is the mass here. Okay. All right. So this is the velocity at burnout in meters per second. Everything is proper units, of course. International. Let me get rid of this. Okay. And the time that the burnout occurs. Sorry, no. The height at which the burnout occurs. We know the time at which the burnout occurs. This is data from our rocket motors. We're gonna see this in chapter 3. Okay. But you can assume. Yeah, I mean, if you have to design your motor, it's hard to assume something now, but don't worry, the dots will connect. Just hold on there. The height at which the burnout occurs is this, and the natural logarithm, and inside we have the hyperbolic cosine, burn time, mass. I think we have K here. Yeah. Oops. All right. And this is meters. Cool. Now we have the velocity at which burnout occurs, and the height at which burnout occurs. Now, what happens in the coast phase? This is let's say the powered phase, the phase in which the rocket is firing. So in the coast phase, it's much easier. Coast. Let's actually move up and put powered here. It's powered. Okay. All right. And then in the coast phase, well, the equation is simplified. We don't have any thrust. And the good thing is that the mass now is the burnout mass, so the final mass. The initial mass minus the propellant mass. The dry mass. Okay, and then we have the velocity again. And we have the weight and drag. And if you integrate this again, by the way, this approximation is much better than the one we did before. As you can see, the mass, yeah, it doesn't change during the coast, so that's all right. The thrust, we don't have it, so good. The only approximation here is drag, which isn't that bad. I mean, it's okay. It can vary a bit, but it's not like we haven't taken the spaghetti approximations we did on the last one. But so if you integrate this, you can find that the time, well, let's see. Let me write the integral real quick so you can see. Oops. So it's going to be this. And we're going to integrate from the burnout velocity to zero velocity. This is the apogee. And so we will start counting from 0 to Tc, which will be the time of coast. Okay, so this is not the time of apogee. Apogee time would be time coast plus time burnout. All right, so we have dt here. And if you integrate this, this should be time coast. This guy here, and then you have the arctangent. Of VB. Okay. Burnout mass and G. All right. And if we do a simple change of variables, say if you take dv dt, and if you do the chain rule, is equal to this is y. Okay, chain rule, simply. And this guy over here is just the velocity again, dy dt, derivative of position. So yeah, we have v and then dv dy. So if we do this change of variables and we substitute this with this up here, here, okay, we can integrate in function of y, dy, yeah. So I'll leave this for you, but you can find that the altitude of apogee, this is coast altitude of apogee will be mb. Well, let's be consistent. We put final mass divided by 2k and the natural logarithm of k vb squared burnout mass g plus 1. Okay. So with this, all these equations, oops. First you have to solve these two, all right? And yeah, and then these two, and then you can add up the times and the altitudes, and you can find the apogee. The apogee your rocket is gonna reach, and the time it's gonna take. So it's nice because you can have like an immediate answer to. You can just test it like in one iteration if you want, and play around really quickly just to check sensitivity of the variables, and that's a big advantage of analytical solutions, and you shouldn't discard them at all. I think also it's a good way to validate. Analytical solutions are very important to validate numerical solutions. So even if these we've taken like really big simplifications, these solutions are going to have to be order of magnitude at least similar to the ones you're going to obtain with a numerical solution, which is way more complex. And so you'll think, yeah, but still, why? If you already have a numerical simulator, well, why would you take this? It's taken a lot of approximations. Well, because basically you're going to have to write your own simulator, and how are you going to know if in that monster code you're going to do, maybe you just messed up a digit somewhere, and how do you know how can you validate your simulator? Well, you can always compare with analytical solutions. Okay, and the solutions will have to be order of magnitude similar to the ones that are analytical in closed form. So I took all this idea of integrating the equation of motion from a book called, let me write it down here. I love this book. This is a fantastic book. Let's see. Okay. It's a book called, if I recall correctly, Topics on Advanced. I think it's model rocketry, but I'm not sure. Let me check real quick. Yeah, that's right. Topics on Advanced Model Rocketry. So, and this is by Mandel. I think it's, well, let's put it, yeah. But I love this book. This is a great book written back in, I think, early 70s, when model rocketry was, I think it was a newborn. So it's an excellent book. It's really hard to get your hands on one of these, but because these guys wrote them when they were like in their masters, I think, or they were pretty young. Actually, I talked with Mandel quite a few times, so we discussed stuff like stability, and I had there's some things that I wasn't, we didn't. I thought that there was a kind of an error in some part of his book, so I talked to him about it. So I'm going to discuss it. Let's see what you think about it. But I've talked with him. He's a great guy. So he 40 years after writing this book, he still remembers his stuff. So that's incredible. And this book is so good because it's so well written. It just for beginners, it's the best book you can start with, because it starts from the absolute basics. You can know nothing about rocketry, and it's going to tell you, it's going to slowly introduce you to everything. Super well written. I really recommend it, and it's all analytical, an analytical study. So yeah, they talk like, yeah, you could do it with a computer machine to get better results, but yeah, 70s. So that's a good thing about this book. There's a lot of analytical analysis. Even yeah, there's analytical analysis and kind of complex stuff like stability with rolling rockets. You're gonna see the math there is pretty tough, but still it starts from the absolute beginning. So you can it's really easy to follow. I really recommend checking this book if you're interested in more analytical solutions like this one. So this one is vertical rocket, non-oscillating, 1 degree freedom with a few simplifications. So I think, if I recall correctly, in their book they have an analytical solution for rockets that are launched at a certain angle, and even an analytical solution for oscillating rockets, which is pretty incredible. So you can, because when it oscillates, the drag is higher, so you have some losses there. So yeah, it's a really nice book. Try to get your hands on one of these if you can. See you in the next video.